Hi everyone, I'm glad to present our work titled In Search of a Data Transformation that Accelerates Neural Field Training. This work was selected as an oral paper in CVPR 2024. My name is Junwon Seo, and this is joint work with Sang-Yeon Lee, Kwang-In Kim, and Jae Lee at Postec. Neural fields have emerged to represent data by parameterizing continuous fields using neural networks. For example, a 2D image could be represented using neural networks by training it with the coordinates of the image as inputs and the corresponding RGB value as target. However, the broader application of neural fields is hindered by high training costs, which are further amplified by the characteristic of neural fields that typically requires fitting for every single signal. For example, training a neural lattice field called NURF can take upwards of 12 hours per scene. This leads us to our research focus: how can we effectively accelerate neural field training? In our preliminary studies, we observed that signals vary in difficulty. When training grayscale Kodak images with a 5-layer silent model, the number of steps required to reach the same PSNR level dramatically varied among different images. This observation is very interesting. Even though the images have the same resolution, the number of steps required for training varies significantly. Why might this be? This question led us to the core of our research. What factor influenced the training cost in neural fields? Moreover, is there a way we can manipulate the data to enhance training efficiency? To answer this question, we considered several different transformations such as node transformation, random pixel permutation, zigzag permutation, inversion, standardization, linear scaling, centering, and gamma correction. And we developed a systematic experimental pipeline. First, we start by applying the transformation to the image data. Next, we train a neural field on this altered data. After training, we convert the data back to its original form using an inverse transformation. The goal here is to determine whether such transformation can indeed influence training costs. Our experiment shows that different transformations affect training speeds in neural fields differently. Counterintuitively, random pixel permutation, called RPP, consistently accelerates training across various datasets and neural field architectures. What RPP transformation does is shuffle each pixel to a new random location, which results in images exhibiting characteristics akin to high-frequency data. Given the known spectral bias of SGD, where networks tend to fit low-frequency components first, this finding was particularly counterintuitive. To explain these results, we propose the blessing of no pattern hypothesis. Simply put, by disrupting the inherent patterns within the image data, IPP removes the low-frequency patterns, potentially leading to a faster capture of finer details and thus accelerating training. We have backed this hypothesis through 3 distinct analyses. The PSNR curve reveals that while RPP starts slower compared to the original data, it ultimately reaches high PSNR levels much faster. This result suggests that RPP removes its to-be-pattern components, which speeds up training in later stages. The analysis of the loss landscape shows that for RPP, there may exist an express way in the neural field parameter space that connects the moderate PSNR parameter with the high PSNR parameter. This linear pathway facilitates a smoother and more rapid optimization process, overcoming barriers that typically slow down training on untransformed data. The loss barriers between two minima are dramatically different: 15.3 dB for the original image and 28.3 dB for the RPP. Errors in the RPP images are more uniformly distributed across pixels, lacking a clearly distinguishable pattern. This contrasts with errors in the original images, which often display periodical or exist online patterns due to the encoding scheme used. These error distributions suggest that RPP prevents the model from overfitting to specific patterns, thus enhancing overall training efficiency. In conclusion, our findings suggest that using data transformations can significantly enhance the speed of training neural fields. This opens up a venue for application where high training fidelity is crucial. Thank you for watching. If you have any question, feel free to contact.